Hello to all of you lovely people out there tonight, and welcome to tonight's episode of Vario Insight Sessions. Today's episode is going to be about improving your performance and deepening the user insights with eye tracking for VR and XR. I'm your host for tonight. I'm Lasse Tuominen, and with me I have Mr. Ferhat Sen, who is a software solutions architect. And as a visiting guest star, we will have Oleksiy Stankovic joining the Q&A session. And Oleksiy is a computational vision developer. Great. So in case you're not already familiar with Vario, I'm a bit surprised that you've even found the webinar, but just in case, here's a quick recap. We're about a preschool aged company, so 5 years, and we're also the creators and providers of the best XR and VR headsets on the market. Our headsets are mainly used in enterprise contexts and are usually known for the amazing human eye resolution and HD pass-through that we provide. But another really important part of that enables the level of quality we provide is the eye tracker we have integrated to all of our models. And today we're going to learn a bit more about that. So one thing to note is that you can submit your questions already. So please look for this sign or this icon in the Zoom tool, and then just start typing the questions and we will answer those at the end of the webinar. If we can't answer all of the questions, we will try to answer those later on in our blog post that you will see come in quickly after the webinar. But now I would like to hand over to Ferhat.
Yes, thanks, Lasse, for the quite amazing intro to Vario. Well, today we will talk a little bit about deeper on the Vario's integrated eye tracking and the automatic interpupillary distance adjustment. And we can maybe start slowly a bit more on what it means and why would these two matter? Like why would eye tracking and automatic IPD, interpupillary distance adjustment matters? As you do probably know, the interpupillary distance is the distance between humans' two eyes. And it's quite unique to everyone. Everybody has a different interpupillary distance. And especially in virtual reality headsets or in wearables, including the glasses, the IPD does matter quite much, because when you wear a VR headset, you would want to have the displays inside the headset to be aligned with the user's eye. And since everybody has a different IPD measurement, then you need to set it up for every particular person. And usually most of the current headsets out there does this manually, and you need to do it manually. You need to know your IPD and do it manually. But with Vario, we have the automatic IPD adjustment, which gives you a few benefits, including like reduced error in setup and fitting. For example, when you wear the headset, the Vario headset knows where your eyes are. So for best visual experience, it lets you know how you need to move the headset, how you need to position the headset in your head by looking at your eyes and recognizing if you need to move it up or down a little bit. And it also saves time in scenarios where you need to switch between the users. Think that you have like a user testing scenario going on, or you have a demonstration going on, and there's 10 to 15 different users aligned in the queue, and you need to switch between the users. What we would need to know is first the IPD value of every particular person, which is not practical in so many cases. And then once you know, then the person needs to adjust it manually once he or she wears that set, or you rely on the person's ability and instincts to set it up for themselves, which again takes quite a lot of time. With auto-IPD adjustment, that's already out of the box. Once you wear the headset, the IPD, the displays in the headset automatically moved by the motors in the headset and comes aligned with your eyes. And this also comes with a drastic reduction in simulation sickness and eye discomfort. This is one of the biggest benefits of having the IPD correct and having the auto IPD doing it for you, because think that you would be trying to look at two displays which are over here, and my eyes would be trying to look like this, which is quite discomforting. So the auto-IPD adjusts it for you, aligns it with your eyes, so that you would have much less simulation sickness and much less eye strain and discomfort. And also the IPD and eye tracking is quite valuable, especially in the research context. So if you are doing any type of research using eye and eye tracking, then you would want to have the IPD to be correct, and you would want to be able to track the eyes with the same setup that you do have. And of course, lastly, the eye tracking enables foveated rendering, which we will go a bit more on later.
Yeah, okay, thanks. Exactly. So can we, that was a kind of a mouthful on the IPD. So should we go a bit more into details on some of the other basics?
Yeah, sure. Thanks, Lasse, for the question. Well, foveated rendering is basically, it uses the eye tracking to render the image in full resolution. And to render the full resolution in the areas where the user is looking at, and reducing the image quality in the peripheral areas where the user is not looking at. So this is basically how human eye normally works, because you just focus on a certain area and you just are focused in the area that you are focused on, and the periphery is not necessarily that much relevant. Of course, this is only possible if you have low latency eye tracking, because think that my eyes are looking top left and the computer is still thinking that my eyes have been looking there and trying to render that part of the frame, although my eyes have been there already, so I know that the render frame is coming late. And usually the 50 millisecond is considered to be the threshold where the human eye would, or human eye and brain would notice the foveation, meaning that if it's beyond 50 milliseconds, then you wouldn't be able to make proper use of foveated rendering. And in Varjo's proprietary eye tracking technology, we have 35 millisecond end-to-end latency, which is fast enough for getting the foveated rendering to be proper for your good user experience. And from end-to-end latency, I mean from the pupil change to the eye tracking results being available for the application to render. And of course, this comes with the reduced computational load for the GPU and the CPU, for the computer graphics and the processor in the computer, because the high resolution displays in the Vario headsets, the application needs to render like 20 megapixels at 40 frames per second, which is pretty high, which is pretty hard to achieve. In order to have the high resolution feeling experience in the headset, but still have a reduced computational load, you use foveated rendering, so that you render only the parts that are relevant for the user, where the user is looking at, and you reduce the image quality on the peripheral areas, which is automatically done by the Vario headsets. And this is, of course, all possible with the help of Varjo's proprietary eye tracking technology, which enables the integrated eye tracking with 200 hertz with sub 1 degree accuracy. From 200 hertz, I mean, we are able to track the eyes 200 times per second, so that whenever your eye moves, even very shortly, we would be able to recognize and track with the 200 hertz eye tracking system that we do have. And of course, this is completely custom made complex IR illumination clone pattern that we have integrated, that we have developed hardware-wise and software-wise to Vario headsets. And again, yet another unique feature is the calibration. So whenever you measure something, you need to calibrate that in order to get a proper measurement. And for eye tracking, calibration has been an issue, or has been there from the very beginning. But with Vario's unique rapid single dot calibration, or one dot calibration, what you need to do is just look at a single dot. As soon as you wear the headset, a single dot appears in front of your eyes, and you just look at it, and in blink of a second, you would be already calibrated. The dot turns into green, and you are ready to go for foveated rendering or any other eye tracking application. We have alternative calibration or foveated rendering methods, which we will go through throughout the slides. But just so you know that we have single dot calibration, which is rapid, that would allow you to have accurate eye tracking results. And all of these data is available for you using our API, Vario API, that you can access to, which we will go deeper. But before we go deeper, one privacy tip I can share. Since eye tracking data is a personal data, so you would want to make sure that you take care of your users as a developer, or when you ask people to use the headset, you would want to make sure that you respect to the privacy. So what you can do actually in Vario-based software is to allow the applications to access the eye tracking data or disallow. So you can enable or disable this option, so that even though the application tries to access to the eye tracking data, if you don't allow it from Vario-based, they cannot access to that data.
And that's always important. But all of these numbers and stats, they sound really impressive. But what we did with Ferhat earlier, we had a bit of a play around with the technology. So we can now show you what it actually looks like on video. So what you can do with it is even cooler. So let's go with that.
Yep.
Right?
Let's have a quick look on the use case where we have air traffic control tower. And here you see an orange circle in the middle that's representing my gaze, indicating where I'm looking at. And as you see, whenever I'm looking at this so small little airplanes in the floor plan, they are highlighted into yellow. Or when you look at the CCTV footage, you would be able to highlight, and within user input, you would be able to use it and select it. And with the time zone chart indicating how accurate the eye tracking could be, even though the very small slice of the time zone areas would be able to be highlighted with the eye tracking feature. And you can zoom in, zoom out. Of course, these are the basic input modalities that you can enable, that you can use eye tracking to implement into your application.
Before you show the next video, I just have to say that, okay, I'm a 37-year-old Star Wars fan. So when we did this video, it was kind of impossible for me not to do movements with my hand and play around with the force. So just a caveat that I'm controlling everything with my eyes here. So yeah, let's move to that one.
Yeah, earlier today we were experimenting a few things, but let's see the single dot calibration, how single dot calibration works. So as soon as last wears the headset, this kind of a view comes up, and you look at the dot for less than a second, and there you go, bang, are calibrated. And here we see Lasse is moving the sphere in 3D space in XR using the focus distance data that's provided. So whenever he focuses to my hand versus whenever he focuses to the light in the background, that the sphere is is basically moving based on where Lasse is looking at with his focus, not the location, not the direction, but the focus distance. So here I bring myself, so he looks at my hand, and then from there on, he looks at the virtual cube over there, and he is able to blow the virtual cube apart. And here in this one, he focuses in his fingers, and this sphere comes closer to him, and he focuses to the further away, and the sphere moves away from him.
Great, thanks. Now, how about the actual data that is produced?
Yeah, well, let's go a bit deeper on what eye tracking data is produced, and what kind of data that you can use using the Vario eye tracking technology. And first and foremost, it would be the gaze rays. From gaze rays, I mean the gaze vector. So wherever your eyes are looking at, and this is provided as a left eye, right eye independently, or as a combined gaze ray for ease of use, so that you don't need to calculate left and right combination. It's a weighted combination of left and right with a single combined gaze rays. And of course, then the distance to focus point, which means is the distance between my eyes and wherever I'm focused on in 3D space, just like in your sphere video that we have seen, that you use the force of the mind control, but using the eyes. So this works within 0 to 2 meters, and from 2 meters onwards, it's basically like infinity. But you can focus on certain parts in the 3D space and be able to understand where the user is focused in this 0 to 2 meter space. The next one would be the gaze focus stability measure, which basically means whether the user has been fixated on certain part or certain point in the 3D space or not, whether the eye is flowing or whether the eye is fixated. This is also quite useful parameter that you can utilize whenever you want to study the eyes, and get the eye tracking insights from the eye tracking experience. And next one would be the status of the eye. Of course, you would want to know in what condition the eye is at a given time. And that would be there are 4 main states. So for the first one would be that the eye is not tracked and it's not visible. So this means that like eye is shut, for example. And then the other would be eye is visible, but it's not reliably tracked. For example, this could be when you blink, or there's some reliability issues with the tracking. The other one would be the eye is tracked, but the quality is compromised. So the accuracy of the tracking is not exactly as you would want. This could be a case when the headset has moved after the calibration. For example, if it has severely moved, you can be aware of this thing as a developer or as a user of the Vario eye tracking feature. Then you can understand whether you would want to warn the user, saying that please wear the headset or please reset the headset in your head so that you can have a better eye tracking calibration. Or lastly, the 4th state would be that the eye is being tracked. So that's the clear green light go kind of a situation. And lastly, maybe we can talk a bit about the eye measurements that we provide with our API, eye tracking API. So as soon as you start using our eye tracking features, you would be able to get the interpupillary distance for the user. So this could be ranging from 58 to 72 millimeters. That it would give you the interpupillary distance of the user, and also the pupil and iris diameter. This would be provided in millimeters again. This is quite unique to the person, and you can use this data to basically measure the cognitive load of the user in that particular time.
So wait a minute. So basically, you could start thinking about measuring like dopamine and noradrenaline measurements through kind of derivative stuff. But okay. Anyways, one question that because you mentioned that both eyes are kind of providing individual data. So do you get the data for both eyes individually as well produced?
Yes, exactly. So you can get separately the data of the left eye, the condition of the left eye, and the condition of the right eye for all the features like the vector of the gaze ray and the gaze and eye location. And you can also have it as a combined gaze ray, which basically gives you a single one if you are just want to be easy to use developer.
Great. So there's a lot of data points, but how do I access that?
Clear question. Well, there are basically two different ways to access the eye tracking data, and they are pretty unique to each other. And we can like go through each of them separately. First one would be using the Vario-based gaze data logging tool that is out of the box, and it's a no-code solution, and you don't need to implement anything to your application. It works out of the box. You get Vario-based with the Vario headset, and you open the analytics window, which we will soon see a video, and you just use it out of the box with any VR or XR application that runs through the Vario headset. This could be, for example, an OpenVR application that's on Steam, or OpenVR application that you have developed, and it's running through the Vario headset, and you would be able to get the gaze analytics or gaze data, from the application. Or if in case you have an app that you don't have a source code to, so you don't have the source code to, then this would also be useful because you cannot really implement the eye tracking if you don't have the source code. But since you are able to use Vario-based, you can run the application through Vario-based's gaze data logging feature, the gaze data logging tool, which then would allow you to utilize eye tracking with the application that you do have.
Okay, and for clarity's sake, Vario-based is the software that runs the headsets.
Yeah, exactly. It's good to point out. I assume that that would be known, of course. But yeah, Vario Base is the Windows software that makes the magic happen in Vario, so that you can control all the features of or most of the features of the headset using the Vario Base, and that comes together with the Vario headset.
Fantastic. And now let's look at a concrete example of using the Vario Base.
Yes, particularly the eye tracking section of the Vario Base. So here again, we are seeing Lasse wearing the headset and single dot calibration kicking in. And soon I will enable the beautiful eyes of Lasse through the eye camera, which you can also do whenever you have a user in that shows the actual eye camera view. And you can enable and disable the gaze dot, which, as you see in this video, is represented as blue dot. So this is real time coming out of the box from Vario-based software, and you can see also the eye camera view of Lasse at the same time in sync with the blue dot moving around based on where Lasse is looking at right now.
And one thing to mention that I don't see the blue dot here. It's just there on the recording, right?
Yeah, exactly. The user in VR or the user in the headset inside the headset doesn't see it, but the external viewers through the Vario base is able to see it. We can maybe mention a little bit about the foveated rendering and related to the calibration methods of which we recently released. So normally we have a single dot calibration, which always automatically triggers and it always calibrates. But there are certain cases where you would not want to do it all the time, or every time that you wear the headset. So that's why we have the remember my calibration feature, which you can select and do the calibration once. And once you do the calibration, the Vario base will know and save your calibration profile and will not ask it again unless you trigger and start the calibration process too. The second option or the third option is basically the best estimation without calibration. So this means that you will use the best estimation of the calibration profile and without requiring the calibration. That would be quite useful in situations where there's like so many people that you want to show the headset to, or that that needs to use the headset, but you would be able to be okay with a bit lower accuracy eye tracking feature or lower foveated rendering feature. This would be a good option. Or you can select never calibrate, which basically fixes the foveation only to the center of the view. It's not going to be moving based on the gaze.
Okay.
And this came out of a request from several users to be able to save the calibration. And now we will soon, as I mentioned, you can enable and disable the gaze dot. Here we have now the gaze dot available, and we can see that Lasse is looking at his ring. And
I just wanted to look at my ring so that all you single people watching know that I'm not single anymore.
Exactly. And then when you click the gaze dot, it just disappears. Eye tracking is still available, it's still working, but the gaze dot representation is not being shown. So what if you want to log this data? What if you want to record this data? So in order to do that, you go to the analytics window from Vario Base and open this small little drawer over there. And it opens up this menu on the bottom where you would see the eye tracking section in a close-up like this. And it says calibrated because Lasse is wearing the headset at that moment. And when you click that one, you would either choose to show the gaze data in the video or not show the gaze data. And you would choose to create the eye tracking, log the eye tracking data while the recording is taking place. And as soon as you choose that one on, then you see the record button changes to a eye icon or changes to an icon with an eye representation. That would show you that, yeah, the gaze logging feature is enabled now. And once you are ready with everything, you press the record button in a second. Ding. And voila. Now it's recording, as you see on top left. You see that the data is now being recorded. This session is now being recorded, which means that you are going to get a video file, MP4 video file of the same view that we see right now on Vario Base Analytics window, as well as a CSV file, a comma separated value file, which basically a text file that you can process. And they are having the same name. So right now we are looking at the video file, which is an MP4. As you see, it's the exact same session that we have just recorded with the gaze.on. And we close, and the other file that's generated right at that moment is the CSV file, which you can see it looks like this. But then, of course, you can process this one and have the insights too. And all of the available data is over here. Like the focus distance, gaze rays, XYZ coordinates of the gaze rays for the left eye, for the right eye, for the combined gaze ray, and basically all the data that you get. And we have a developer documentation which goes and explains this quite in good detail. One thing I would like to explain more in the gaze data format is that there are two types of data in this CSV file that you get. First one is the generic gaze data, which you can also acquire or which you can also access with the Vario APIs. And the other one is the video capture related data. This is specifically for to be used together with the video capture that comes together with the session recording, so that we provide you the projected XY coordinates, which can then be used to directly map the gaze coordinates to the video's pixel coordinates. This is just for ease of use, that you can sync them with a timestamp of the CSV of the frame for each frame, and then you can sync them with the video quite easily for the easier analysis. And in the developer documentation, everything is pretty much explained in great detail. All the states which I have been explaining a few minutes ago, the states of the gaze and left eye, right eye, pupil size. And this part is the video capture related data, as we see, and we can get the projected coordinates to 2D space that is easy for you to map onto the video file created. And then lastly, let's have a look for a bit better accuracy eye tracking. So in case you would want to do a research, and in case you need a higher accuracy, you can use the 5-dot calibration, Vario's 5-dot calibration, and you can trigger it from the calibrate button, which is over there. And as soon as you click to that button, again, a calibration screen appears, and you just need to look to 1 dot in the center and 4 dots in the corners, which would give you the 5-dot calibration with a higher accuracy eye tracking results. And this is especially useful in situations where you would need higher accuracy in the research contexts. And voila, the 5-dot calibration is done. Again, the same thing. You are still calibrated again the same way, but with a higher calibration profile, it would give you a higher accuracy.
Great. Now, just in case I'm a CSV intolerant person, or I just want to do things more easily, you mentioned that there was an API.
Yes, there actually is, and we can have a look at that one. So the second way to access the eye tracking data, first one was the Vario base. So it's a no-code solution. You don't need to implement anything. As long as your application runs on Vario headset, you would be able to use that with the Vario's gaze data logging tool. And as I mentioned, this could be especially useful in case you don't have access to the source code. And as long as your application is working by OpenVR, OpenXR, or natively supporting Vario, then you would be able to use the Vario base, the gaze logging tool. But if you want to have a bit deeper control, and if you want to have a bit direct access, we have the Vario's API, public API, that would allow you to access all the data that I mentioned that we've been through. And there are different ways to use it, utilize it. We have the native SDK, which you can start right away, integrating into your own application, C++ application, that you even have a sample project that you can quite easily start experimenting. We have the Unity XR SDK via the Vario plugin. So you could actually get the same data in Unity using the Vario plugin. And then we have also OpenXR support via the OpenXR iGaze interaction extension that would allow you to implement Vario's eye tracking features in OpenXR applications or in Unreal-based OpenXR applications. This would allow you to get the data, though the OpenXR extension is a bit smaller in scope than what Vario could actually provide. But you still get the gaze data there, but not exactly all the data that you would actually get if you would use the native SDK or Unity XR SDK.
Okay, so I know that you have a cool example of actually applying this. So can we look at that?
Yeah, let's have a quick look. Once you get the data into your application, what you would need next is, well, how to make sense of the data. I mean, you would like to kind of analyze. You would need to analyze the data to make sense, and there are different ways to do it. There are third-party eye tracking analytics tools, which, for example, Cognitive 3D is one of them. And that would allow you to integrate, easily deploy to your application, your existing application, because they do have Unity and Unreal SDK, which works directly with Vario eye tracking solution, eye tracking technology. That, for example, you could create a scene, and then you could record that whole session and explore the scene in a 3D-based scene explorer that the Cognitive 3D does have. And you can create these kind of heat maps, for example, that based on where the user is looking at, the color coding of the location where the user is looking at becomes hotter compared to cooler. And this, again, of course, is a third-party tool which you can utilize and implement into your application, which then would give you also the same things like the gaze direction, fixation, whether you are fixated into certain parts in the scene, or also the pupillometry data, which means basically fluctuations in the pupil diameter, which would give you the cognitive load in that sense, or any other stimulus that is being given to you and being visible through your pupils.
Great. Next, we're going to move into some actual use cases. And just a reminder, because I see that there's a lot of good questions coming in, but just a reminder, if you have questions, there's a small Q&A icon in the Zoom. So just click on that and then type your question into that session. But next, let's go to something that's actually available straight from our demo bank. Once you purchase your own headset, as you all will, then you can download some demos, and this one is available there.
Well, yeah, one of the use cases is, of course, in eye tracking in VR, especially has been in consumer research, especially in the retail context. As you see here, you would be able to, when you 3D scan a supermarket, you would be able to study where the user is looking at. And you can study consumer interactions with the store layout, try different layouts. And this would even make much more sense with the Vario's human eye resolution, because those store environments will look almost like you would see it with your own eyes with the Vario's human eye resolution displays, that you would be able to read the text that are on the packages or that are on the price tags. With this way, you can optimize the packaging design. This has been used quite many times, or you can observe and optimize the whole buying experience, whether in a supermarket or in a showroom. For example, think that you have a car showroom and you have a couple of different layouts which you want to study with the users to see how users would respond to different locations and different orientations in the showroom. That would be one use case. Or if you want to, for example, study the wayfinding designing a wayfinding solution for an airport, and you place certain arrows and certain direction panels throughout the virtual environment or in a real environment too, then you would be able to analyze which design would work if you want to compare, and you would just put the users into VR or XR. Then you would be able to check and confirm whether your design decisions has been accurately represented by the actual users.
Yeah, exactly. Like A/B testing in real world examples or use cases. And like you said, product design should be wowed about this, really, because they can start figuring out which which product design really catches the eye of the potential customers. There was also a nice partner example that we had on medical side. So let's look at that next.
Yeah, actually, medical training simulation is also another area where VR in general has been beneficial for providing training in a fail-safe environment. So basically, because it improves task memory and minimizes the remembering or recall errors. But then you would want to measure also not just the task completion time or not just completing the tasks, but to be able to measure the cognitive engagement of the users to compare two successful trainees, for example. During a test, during the training, you have two trainees which have succeeded successfully the training, but you would then be able to differentiate the which successful trainee is a bit more successful than the other based on the cognitive engagement and the cognitive load during the task. Or you can get deeper insights and you can have objective performance feedback. For example, how many times the trainee has looked to the certain or fixated to the certain tool there, whether it's like more than how she should be spending time with or not. And this is all possible, for example, using the iMotions data analytics tool or eye tracking analytics solution, which is again a third-party solution that works with Vario headset. So when you have the Vario-based video recording and then gaze data as CSV file, you just load it to iMotions and you can get really deeper insights and you can analyze quite easily the data that you have at hand.
Yeah, you could also like not only compare trainees, but you could record like a superstar surgeon first doing the same operation, then compare that to the trainees and see how those kind of two experiences differ. You mentioned earlier about academic research as well and how IPD is important, but I guess the eye tracking in general is also important.
Yeah, exactly. In the academic research context, Virginia Tech researchers used our native API and developed a gaze-based interaction to use eye tracking as an input modality, which means that you will be able to, for example, zoom in by like closing one eye and zoom out by closing the other eye without using your hands. And you would also be able to, they also studied the way to interact with the menu using the eye tracking feature to change the zoom levels, for example, here, and be able to go back to the normal view with the eye tracking, again with the eye as an input modality. And this has been used as a dynamic magnification tool so that you would be able to have the hands-free magnification and your hands will be free. And this could be a use case example in a clinical setting. So they use the VST, video see-through cameras of Vario headsets, as you see there, and use the gaze interaction as a surgical eye loop. So if you know those surgeons wear those like magnifiers into their glasses, which they can see quite detail in the areas that they are doing the surgery to. And in this particular case, they are able to, the surgeon trainee is able to see and control the zoom level and control zoom in and out without using his or her hands.
Nice, thanks. So simulation is one of the biggest use cases and biggest customer areas that Vario has. So let's have a look on an example how eye tracking is utilized there.
Yeah, pilot training has been also quite a good area where eye tracking basically shines. In VR simulation, developed this part task flight trainer, where the real-time visibility of the trainees' eye and head movements are visible by the instructor, so that the instructor can review the trainee's real-time performance and is able to then talk about and review in a quantitative way rather than in a subjective way. To talk about it here, as you see in the video, there's this blue and red rays that are going out from the cockpit, and those are the representations of the pilot's eye and the head and the eye at the same time. That would then be quite good. That's then useful in when the instructor, for example, wants to review where the pilot's attention was during a particularly important move in the mission or in the training, or they can identify areas for improvement quite easily because they are aware of what needs to be done in that particular moment, and this is right away real time visible in front of the instructor's eye, where the actually pilot's eyes are.
Well, that's been a lot of interesting use cases. So thanks, Varjo, for going through those. I think that was the last one from us, right? So next it would be time to jump into the Q&A session. And we will be joined by the super special guest star, Mr. Oleksiy.
Hi, everyone.
Great. So what we'll do is that I'll first read through the questions, and then these guys will answer them. And in case we won't be able to answer all of them, just as a reminder, we will answer them later when we release our blog post after the webinar. So stay tuned for that. So first one, it's from Ben. Does Vario plan to track eye openness as part of its eye tracking? If so, when does Vario plan to implement it?
I can say that eye openness is very important for social VR applications, and it's in our backlog. So stay tuned, it will appear.
Great. Next question. What is the current latency of the eye tracking, and how does this limit what the capabilities are of the system? And how will this change in the future?
Okay, current latency of eye tracking can be actually measured. Important to know that the timestamps that we support together with eye tracking data approximately correspond to start of camera exposure in eye tracking cameras. So you have all possibilities to measure the latency on your system. We have only just our estimates from a typical compliance systems. So it takes usually about 12 to 15 milliseconds to get eye tracking data through native API, for example, to your application for a typical compliant computer, but you have all the means to measure it on your system.
Great, thanks. I've seen a few of these questions, but what about eye tracking with glasses or spectacles?
Eye tracking is less accurate with eyeglasses than without eyeglasses. But Vario supports all the common types of eyeglasses, and the accuracy is of course worse. But usually users should avoid blocking the LEDs, infrared LEDs that are important for eye tracking. With, for example, thick eyeglasses frames or some uncommon eyeglasses frame shapes, and a lot of attention here to headset alignment.
How about the IPD? Does that also work with glasses?
Auto-IPD also works with eyeglasses. It might be less accurate than without eyeglasses because distortion caused by extra lenses, of course, impacts the estimation. But it's supported.
Okay, great. Then there's a question about how do the different eye calibration techniques differ? And then a continuation here is that there is one method that wants me to look at the single point, putting the Vario in, and then there's the 5-point calibration. So why are there two methods? I guess we actually answered this, so that's the kind of quick one, and then the more accurate one, but...
Yes, so the best accuracy you could get with using 5 dots calibration. So that's the best eye tracking accuracy that you can achieve is using this method. So we recommend to use it. 1 dot is a faster way. Then we also have another type that was not yet mentioned. It's 10 dots calibration. It's available only through Vario API. And the difference that it doesn't use, comparing to other methods, doesn't use any statistical or trained model. So it uses only the input from the current user and might be interesting to medical research applications, for example. But for regular usage, we recommend 5-dot calibration as the most accurate method.
Next question is on diopter adjustment, if not using glasses.
At the moment, we recommend to use glasses if user needs to do so in real life and in eye track and no support for the optics adjustment.
Okay. Can you customize the calibration if you're using it for research purposes? I guess that's the 10 dot.
Yes, 10 dot, it takes input only from current user. It doesn't use any trained or data for training gathered from other people, like all the other calibrations. So we recommend it for medical research use cases, but all other lesser calibrations like 5.1 dot and best estimation, they heavily rely on population collected data. So they are recommended for typical usage.
Okay. Are all of these features supported in the OpenXR specification?
Unfortunately, at the moment, there is only one extension supported by OpenXR. It's gaze interaction. It's basically a very simple one. It provides the only combined ray and focus position. So Vario contributes to extending OpenXR specification together with other big vendors like Microsoft, Facebook. So a lot of companies contribute together, but it takes time to agree and deliver new cross-vendor extension. In our backlog, we have plans for various specific OpenXR extensions, so stay tuned. This will be delivered at some point.
And as you know, if you want to use something via OpenXR, there needs to be an extension for it, just as a background. So you need to have the OpenXR extension to be approved by the OpenXR consortium, and then the vendors, and then the engines or the plugins would need to support that those features in their application. So it takes some time to agree on, and then also to release. So simply because of the OpenXR's own unique intrinsic processes, it takes some time. But we are working on it, as Oleksi mentioned. We are working on it as a dedicated extension.
So now there's a question a bit more deep into it. So how does the eye tracking algorithm work? Is it a neural network, or what methods are used to train it?
Unfortunately, I cannot answer this question here. It's implementation details. Sorry, guys.
Okay, thanks. So then is it possible to do the one dot calibration in an external program?
At the moment, through Vario API, we do not support triggering one dot calibration from external application because it was always system specific, like Vario system specific calibration. So user puts on headset and it's automatically triggered. But through Vario API, you can trigger 5 dot calibration and 10 dot calibration.
So does it measure pupil dilation as well as direction?
So we have in public API, we have provide access to pupil dilation data. So you can get this data through API and also through gaze data login feature in Variobase.
Then a question of the combined gaze rate. So where is it measured from? Is it from the middle or from the kind of middle point between the eyes?
Yeah, so the current model of the eyes is such that origin of the combined ray is always in 0, 0, 0 coordinate. Left eye is always in minus half APD by X, and right eye is in plus half APD by X. So this is kind of a simplified model to represent eye's position in VR world. But yeah, this model is fully accounted in the gaze data that we provide, in the gaze rays that we provide through API. So that's how it is at the moment.
And is it possible to calibrate with only one eye?
At the moment, there is a limitation that in order to pass any kind of calibration like 1 dot or 5 dot, user needs to focus at the dot with both eyes stably for at least half a second interval. So user cannot pass calibration with just one eye at the moment. But once user is calibrated, then eye tracking data for each eye is available independently. So each eye is calibrated independently, but there is this limitation for 2 eyes at the moment. If a user cannot, like if there is some medical condition, disease, that user cannot focus on the dot with both eyes, we can recommend using best estimation which provides eye tracking data even without passing calibration. It's less accurate, but it doesn't require user to pass calibration.
Then a bit of our future view. So do you guys see that the advanced eye tracking solutions will eliminate the need for physical trackers or controllers?
Wow, it's a question, actually, a good question also for design team. Unfortunately, I don't. Yeah, it's a design team. We don't have them there, but yeah, I can imagine. I can think of possible cool and crazy at the same time ideas how to do it. But I'm a tracking developer, so I'm focusing at the moment on eye tracking. So maybe that question can be answered later offline.
Yeah, it's probably like you have seen with the force video, last year's force video, and also the air traffic control tower video. That you can use the eye as an input modality, or eye tracking data as an input modality for creating interactions. But again and again, it's more of a research area and coming up with gesture-based interactions, or specifically eye gesture-based interactions. That's a dedicated topic that that researchers are working on, and we are kind of following them what they are doing with the headset especially.
And then a couple of questions on the foveated rendering. So what's the resolution inside and outside the rendered area?
Oh, I don't remember from the top of my head, but you can always refer to documentation on our website. I think we document in detail all these aspects.
Yeah, I would strongly echo what Oleg mentioned. Yes, we don't remember on top of our heads, but yeah, that's already in documentation that you can. Developer.vario.com would give you the right answer.
And then there was a continuation question on how much control does the user have on the foveation? Can you turn it off, and can you, or is it always on?
I think we have this different, it was already in presentation, we have the different modes how to calibrate for foveation. For example, you have this one mode, never calibrate, which means that your foveation area is always locked to the center. So why, you might think why you need it. For example, for video shooting through lenses, that in order not to make eye tracking algorithm try to find a pupil in the view of some external camera, we have exactly these options. And also there are other options like remember my calibration and a best estimation without calibration and always calibrate. So these are always how to calibrate foveated rendering.
Okay, so here's kind of a specific one. So because some people have like drift or lazy eyes, so when they are looking at some specific dot, their muscles in the eyes kind of get laxed. So what happens when that happens?
Okay, we of course don't in the algorithm we do not try to auto-assess if the person has some medical case or doesn't have some medical case. So the algorithm will try to track the eye as if it is healthy. So this means for lazy people or for nystagmus people with nystagmus condition, there might be fluctuation in the gaze rate that is delivered. But as already said, you always have access to individual eye data, so you can switch, like consume left or right eye data in your application, and also do some data analysis from that. But we do not try to not track the eye because it misbehaves.
Yeah, you can detect basically those conditions in your own algorithm by using the data that's provided by our API. And then you can filter out and have alternative solutions just to focus on one eye or bypass for a momentarily if those kind of situations takes place. So it's provided, data is provided, but you need to have the algorithm to recognize those and to apply actions on the fly.
Then there's an interesting question about eye tracking and utilizing that for avatars or facial expressions. Have we made any research on that?
Oh, so for facial expressions, as I said, we have in the backlog eye openness factor. So stay tuned. It's one important delivery from eye tracking. But you should realize that we see only very limited amount of user face through eye tracking cameras. So we cannot really track all the emotions from that.
This is very research specific. So In research cases, it's important to know the details of certain parts of the eye tracking algorithms used. For example, the basics of to classify the eye movements, fixations, and saccades and other features. Are these sorts of informations available for researchers?
So we deliver eye rays, and you can do any analysis on top of the eye rays. So you can try to analyze for saccadic movement. There is one important note about the data filtering. So for scientific research, for medical research, and you might be interested to turn off the smoothing of the eye data. So you can apply your filters on the raw data, implement your own filters on the raw data, and do your own analysis on top of the raw data. By default, gaze rays are smoothed. Default use case is more targeted for interaction and just other common use cases.
And then about the pupil measurement. According to our documentation, it's measured as a value between 0 and 1. But for some research purposes, it would be very important to get it in actual millimeters. So is there any plans to change that to actual millimeters?
Yes, just download Vario 3.6. And you can find that there is pupil estimate in millimeters. This is a new algorithm. You should, it's quite challenging to estimate pupil size accurately in millimeter units because you need to account for different eye relief. So a user might put on headset with bigger eye relief distance from eye to the lens, or with smaller. So you have more pixels or less pixels in 1 millimeter. But there is already experimental algorithm that was released in Vario 3.6, and please try it and send your feedback to us.
Yeah, just use the latest Vario base, which is downloadable right now, and that already has the feature to get the pupil diameter in millimeters, which recently published right out of the oven.
Okay, great. So I see that our director there is pointing at his watch for us. So I think that we're running out of time. So again, thank you, Alexi. Thank you, Ferhat. Has been really interesting to hearing you kind of talk about us, talk about our eye tracking and answering the questions. And regarding the questions, just as mentioned, please remember that we will answer those in the blog post that we will release after the webinar. And if you have any questions other than eye tracking or eye tracking, you can please email us at hello@vario.com. And if you're interested to learn more about our products, you can scan this QR code and download the product book. That's all from us today. I hope you enjoyed, and see you next time.
Yeah, cheers. Thanks you.
Bye-bye.
Thank you. Bye.